Everyone, in this video we're looking at an example of how to calculate an interval estimate for a proportion. So here's our example. In a random sample of students from Red Rocks Community College, 29 out of 47 students are full-time, meaning 12 or more credits. We want to calculate an interval estimate for the proportion of all Red Rocks students that are full-time at the 98% confidence level. So in this scenario, we have a sample proportion, which we call p hat. This is 29 out of 47. And we really want to know what is the population proportion. What is P, or the proportion of all Red Rocks students that are full-time. So our population is RRCC students, and the sample is the group that we actually looked at, which has a sample size of n equals 47, and that sample proportion 29 out of 47, which is about 62%. So I want to remind you of the sampling distribution. So this looked at if we took our population and took many different random samples over and over again. So we're taking a sample and we're measuring the sample proportion. We're taking a sample, measuring the sample proportion, taking a sample, measuring the sample proportion. What we saw is that these sample proportions, under at least certain conditions, will form a normal distribution where the mean of the sample proportions, this is written as mu sub p hat, is the population proportion. So these sample proportions will be kind of centered around, grouping around the proportion of the whole population, in this case that are full-time students. Some might be a little above, some might be a little below. And the standard deviation of those sample proportions, which we call the standard error, follows this formula here, the square root of p times 1 minus p over n. We're going to be approximating this by using the sample proportion in that calculation. So rather than p, we're using a p hat. Because of course, if we're trying to do an interval estimate, we don't actually know what p is. That's what we're trying to estimate. But p hat should be relatively close. So estimating the standard error using p hat gets us an approximation that will allow us to get a reasonable estimate of how spread out, how far away from that population proportion our sample proportion might be. So in this interval estimate or confidence interval, we're looking at our point estimate, which is the sample proportion. In this case, the sample proportion, again, is about 62%, 0.617. And we expect that the population proportion is likely pretty close to that, but it could be a little above or below because, again, this is a sample proportion and it doesn't have to match the population proportion. The standard error here, or at least our approximation of the standard error, is going to give us an idea of how spread out are p hats from different samples. So here we got 0.617. If I took a different random sample with size 47, how far away would we expect that to be? Now, obviously, this is a random process, so we don't know exactly, but the average deviation, or the standard error in this case, is calculated with this formula, square root of p hat times 1 minus p hat over n. P hat is 29 over 47. 1 minus p hat would be 18 over 47, or you could use the decimal versions of each of those. The n value is 47, that's our sample size. And then I'm plugging all this in and taking a square root. This gives me approximately 0.070907. So I'm thinking of this as about 7%. So variation among sample proportions is about 7%, which is fairly significant for these percentages. But that's probably because this sample size is relatively small. Now we are going to use Excel to do our calculations here, so I'm just going to summarize this information. So p hat was 29 out of 47. I'm putting this in a labeled cell in my spreadsheet, so I labeled it p hat, and I'm using a calculation with an equal sign at the beginning so that this will actually calculate 29 divided by 47 and get a decimal value there. I'm also going to compute 1 minus p hat. This is another equals 1 minus, and then I'm going to use the p hat I computed above. That 1 minus p hat is sometimes called q hat. That's essentially the percentage or the proportion of the sample who was not full-time. And then n was 47 in this case. We're going to talk about the critical value in just a moment, but I will include here the standard error. Make a new box for that. So that was the square root. So I'm going to do equals SQRT for the square root, parentheses. I'll take my p hat number times my 1 minus p hat number, and then divide that by 47. And then I close my parentheses to end the square root. And this gives me that standard error that I saw earlier. So our interval estimate is based on the sample proportion and the standard error, but we also need a component called the critical value. And when we're dealing with a normal distribution, which is the sampling distribution for proportions, this is going to be a z-score, or we call it a z-star. And this critical value really represents how many standard deviations away do we want to include. So we're going to do an interval estimate centered around that sample proportion, so our p hat, which was about 0.617. But our interval estimate is going to be a little above 0.617 and a little below 0.617. Our interval estimate is going to be some range of values. So we want to know, we know our standard error or our standard deviation of these sample proportions. How many standard errors do I want to move away, sort of above and below? This is what makes up the margin of error. So in the normal distribution, some examples, these are based on the empirical rule. If your z-star, if your critical value was exactly 1, that would mean that we'd get approximately 68% of possible values within that region. In any normal distribution, about 68% of values in the population, or in this case of sample proportions, would fall within 1 standard deviation away. If the critical value was 2, we'd be getting about 95% of the possibilities. And if the z-star was 3, that's about 99.7% of the possibilities. So this is where the idea of confidence level comes in. We're never going to be 100% sure that we're getting, all the possible outcomes from our interval estimate, because the sample is randomly selected, and most likely our sample proportion is quite close to the population proportion, probably within 1 or 2 standard deviations. But it could be that we just got really unlucky and our sample proportion is way off base because we happen to get way too many full-time students or way too few full-time students. So we can never be 100% certain, but we're using these probabilities or percentages in the normal distribution to help us capture where we think essentially how far away we think the population proportion is. So for this particular example, we wanted a 98% confidence level. That was what the question asked us for. So I'm imagining in a normal distribution, if I wanted to capture 98% of all of our possible values, I'm going to leave off a few of the extreme low values and a few of the extreme high values. And the critical value is the z-score that sort of represents that cutoff. There are technically always 2 critical values. There's a positive one and a negative one on our normal distribution for sort of the highest tail, or the right-hand tail and the left-hand tail. The critical value that we're going to actually find is the positive one. It's the one on the right-hand side. And we want to imagine sort of taking our normal distribution and saying, how can we get 98% or 0.98 area in the middle? So this is just a normal distribution calculation. I'm going to do this in Excel, so I'm going to use the norm.inv function. This is also using the standard normal distribution where the mean is 0 and the standard deviation is 1, because we're just talking about z-scores here rather than a specific population. So if you want, you could use the norm.s.inverse function, which does the same thing, but just with those mean and standard deviations set. I'm just going to use the regular norm.inverse function. And just a reminder, the first input to this function is the area to the left. So since I want to be finding this z-score here on the right-hand side, the area to the left is actually not 0.98. That's just the area in the middle. I either need to do 0.98 plus the area in this lower tail, or I can think of this as 1 minus the area in the upper tail. So when you look at the confidence level, that represents sort of the area in the middle, the part that we're interested in. And we have to chop off, in this case, 2% area in these two tails. This leaves an area of 1% or 0.01 in each one of these tails, remembering that the entire area has to be 1. So the area to the left here is going to be 0.99, which is either the 0.98 plus the lower tail area, or 1 minus the upper tail area, the 1 minus the area to the right. So this is going to calculate the z-score that I want. So I'm going to do equals norm.inv. I'm putting in 0.99. The mean is 0, the standard deviation is 1. So this gives me a z-score a little bit bigger than 2, which is kind of what I would expect from the empirical rule. If I wanted a different confidence level, I can just adjust this. I would do the same process. So say I wanted instead an 86% confidence level, just to give kind of a weird number. Most of our confidence levels are either 90% or 95%. But just to give you an example here, if I wanted an 86% confidence level, I'm imagining, okay, that middle region is going to be 86%. 1 minus 0.86 is 0.14. So that would be the leftover area, and I'm going to divide that in between these two different tails. So I'm going to have 7% area, or 0.07 in the bottom tail, and 0.07 or 7% in the upper tail. So the critical value is going to be the z-score, where the area to the left would be either 0.86 plus 0.07 or 1 minus 0.07. In this case, that would be 0.93, or in Excel, you could just put in 1 minus 0.07 if you want to. So that's how we calculate the critical values for whatever confidence level we want. I'm going to stick with that 98% confidence level, which gave me a critical value of a little over 2. So we're going to take a little more than 2 standard deviations, or 2 times our standard error, and we're going to add and subtract that to our sample proportion. So here's what that looks like as a formula. We're saying that our population proportion, that's the thing we're trying to estimate, this falls somewhere between the sample proportion, that's our p-hat, that's the point estimate, plus and minus what we call the margin of error. That margin of error is the critical value times the standard error. I'm writing this here as an inequality, so I have p-hat minus the margin of error is less than p, which is less than p-hat plus the margin of error. So we have sort of a lower bound and an upper bound here. Lower bound, upper bound. But you can also just write this as like a plus or minus statement. So p-hat plus or minus the margin of error, that's going to give us those upper and lower bounds of the interval estimate. So switching back to my spreadsheet, I have pretty much all of these values already. The margin of error is going to be the critical value, the z star, times the standard error. And I have those both computed already. And then I set up a little, some boxes for my interval estimate. So I'm saying that the population proportion P is going to be somewhere between, on the low end, it would be P hat. So I'm going to do equals, take my sample proportion P hat minus the margin of error I just calculated. And then on the upper end, I want my sample proportion P hat plus the margin of error. So I'm doing two different calculations here with the same numbers, and this gives me a range of values. In this case, this is saying that the true population proportion is somewhere between 0.45207 and 0.78198. And because these are proportions, we often would interpret these as percentages. So this is about 45% to about 78%. We think that somewhere between 45% and 78% of all Red Rock students are going to be full-time. Now, this is quite a large range. This is a big margin of error here, and that likely is because our sample size is fairly small. 47 is not a lot of students to go on for these percentages. But in terms of a statement, we could say that we are 98% sure that the proportion of all Red Rock students that are full-time falls between 45% and 78%. 98% is also a really high confidence level. Again, it's not 100%, but it's quite high. If we had chosen to do a lower confidence level, like 90%, we would see a narrower range of values. That's it for this video. Thanks for watching.